Hello Chem 1A, this is Chapter 10, Lecture Video 6, and we're going to be talking about expanded octet and exceptions to the octet rule. So let's talk about the exceptions to the octet rule. One of them we hopefully already know, which is that hydrogen actually is good with only having 2 electrons around it. There are 2 other exceptions in terms of the less than direction, and that is beryllium actually is good with 4 electrons, valence electrons around it in Lewis structures, and boron's actually okay with 6 valence electrons around it. This is only true for boron and beryllium when they are the central atoms, but they are exceptions you should be aware of. Let's talk about expanded octet. Expanded octet is where we can have more than 8 electrons around the central atom. So these first 3, hydrogen, beryllium, and boron, are examples of where it's okay to have less than 8. There are many examples where it's actually okay to have more than 8 electrons around the central atom. So compounds in which the central atom has more than an octet of electrons are considered expanded octet structures. This occurs when the central atom of our compound is in the 3rd row and down of the periodic table. So it's got to be in the 3rd row of the periodic table or lower, and this is due to the fact that in that case it has empty d orbitals available. And when we go over 8 total electrons in the valence shell, what's happening is we're starting to fill the empty d orbitals present for that central atom. Now that is great, and it allows us to do an expanded octet. Now, does this mean that expanded octet always happens? No, there are definitely structures with a central atom that's in the 3rd row of the periodic table or lower that can be drawn without using an expanded octet. But in most cases, those structures can also be drawn as an expanded octet, and it might be a more stable structure. How do we know? Formal charge. So in the last lecture video, we talked about formal charge, and we even drew phosphate. Now, phosphate's Lewis structure that we came up with in the last lecture video looked like this. In this structure, we found, if you remember, that each oxygen has a -1 formal charge, and the phosphorus has a +1 formal charge, right? So our formal charges are -1 for each oxygen and +1 for the phosphorus. Now, as we learned, due to formal charge, this is actually a pretty bad structure. Every atom in the structure has a formal charge, making it rather unstable. It would be better if we could eliminate some of these formal charges so that the structure is more stable. So in comes expanded octet. Phosphorus is actually in the 3rd row of the periodic table, meaning it can form an expanded octet structure. This gives me a new structure. So instead of drawing phosphorus or phosphate with single bonds for every single one of our oxygens, what we can do is we can move one of the lone pairs on one of the oxygens into a double bond, right? So if we look at this structure, this is the original. It doesn't matter which one we pick. Let's just take this lone pair here. We're going to erase it and move it into a double bond. Now, if we recalculate our formal charge, we still have an overall structure that has a -3 overall charge. And so if we calculate our formal charge for this oxygen, we get 0. We get -1 for this one, -1 for this one, -1 for this one, and we get 0 for phosphorus. This is a more stable Lewis structure. If we continue to make double bonds, which sometimes we might need to do, in phosphate's case, we actually get a less stable structure because the phosphorus gets the -1 charge if we add another double bond, and then oxygen turns to 0. But oxygen is more electronegative than phosphorus, so it's better for the oxygens to have the -1 charges. Notice that we still add up to -3. That is a must. It has to happen. If it isn't happening that way, then we calculated something wrong or we drew something wrong. All right, so let's draw some Lewis structures that are also expanded octet. Now, in phosphate's case, we can draw it with both out using the expanded octet system and with drawing it as an expanded octet. Turns out that drawing it as an expanded octet is better. It's a more stable structure that way. So that's the way we should draw it. Some structures, on the other hand, are not possible to draw without breaking the octet rule. Let's look at some of them. So we're going to do these 3 structures. Xe has 8 valence electrons. Chlorine has 7. There are 2 chlorines here. This gives me 22 valence electrons in this structure. The central atom here is Xe, so I'm going to put my Cl's around the Xe. Next, I need to put lone pairs on the exterior atoms first. I've used up 4 electrons total. I need to make sure that each chlorine here has 8 electrons around it by adding 12 total electrons to the structure, all as lone pairs around the 2 chlorine atoms. Now at this point, you notice that we have used up a total of 16 electrons. We still have 6 electrons left, and according to our Lewis structure drawing rules, which account for expanded octet, we have to put those last remaining electrons on the central atom. So this means I'm going to put 3 lone pairs on my central atom, and if we look at our central atom now, it has a total of 10 electrons around it. It is violating the octet rule, but its xenon is in the 3rd row or lower on our periodic table, and therefore this is an acceptable Lewis structure. If we look at SF4, we can calculate its valence electrons, and we get 34 valence electrons. Sulfur is going to be my central atom because it's the least electronegative, and I'm going to attach my fluorines to the sulfur with a single bond, at least at first. In this case, it'll stay a single bond. Next, I need to put my lone pairs around each fluorine. By doing this, I'm adding another 24 valence electrons to what I had already put on the structure. And now I can count how many valence electrons I've used, how many I have remaining. At this point, we've used 32 of our 34 valence electrons. So we still have 2 electrons left. Those last 2 electrons need to go on the sulfur as a lone pair. This again puts us at 10 valence electrons around sulfur, and this is okay because again, sulfur is in the 3rd row or lower on the periodic table, and so it can form expanded octets. The last structure, BrCl3, has 28 valence electrons. And Br is less electronegative than Cl, so I'm going to put my Cl's around the Br, because Br must then be the central atom. At this point, I've used up 6 of my 28 electrons. I still have 22 more. The next step would be to put lone pairs around each one of my chlorines. This would use up another 18 total electrons, which would mean that I still have 4 electrons left to put on my structure. Those 4 electrons have to go as 2 lone pairs on the Br, which gives me my structure. Again, bromine in this case has 10 valence electrons around it, and this is the correct structure. Now, it's not always 10. I've been using examples where it's 10. Sometimes it's 12. That's pretty much the majority of where we get to, though. We don't typically get more electrons than 12 around the central atom. If you have any questions, as always, please don't hesitate to contact me.